moving on, so we have now gone up to chapter 9 in the Sandler book. So what we've done is we've established the foundational principles of multi-component thermodynamics. So effectively, this was come about by defining a term called the partial molar property. Again, we use this theta to indicate any particular property that we care about. So the partial molar property is how does the total system property, right? The number of moles times by the specific property, the underbar, this will give us, like, let's say volume, if it's V underbar, for example, times by N. What this is saying is that how does the total system property change as a result of adding or subtracting just a little bit of component 1. Now the reason why we care about this is all because of one term, the chemical potential of species I, which can be written a number of ways based on whether or not you have a constant TV system, right? So in this case, this is the partial molar Gibbs energy. This is for a constant temperature, constant pressure system. This could be the constant the partial molar Helmholtz, and for a TV system, those are the two most commonly ones we're going to encounter. For most chemical engineering disciplines using vapor and liquid, which is by far and away the most predominant separation technique that chemical engineers use in the means of distillation, or a flash separator, is going to be constant temperature and pressure conditions. Now you'll often find, if you read the literature in thermodynamics, the Helmholtz energy is extremely popular. This is going to be popular for liquid mixtures. Because in a liquid, you can generally make the approximation that it's going to be incompressible. And if it's incompressible, you're not going to care too much about changes in pressure. The properties are going to be relatively fixed. So if you ever look at literature for polymers, proteins, all sorts of other types of systems, you're going to be generally finding that the Helmholtz energy is the one that's most commonly used, because what's the point of introducing extra complexity? As you can see with thermodynamics, everything is very, very precise. So if we take the partial derivative of a function with respect to two variables, it's vastly different than with two others. So taking the partial derivative with respect to volume versus temperature versus specific volume, those are all different things. So thermo is extremely precise. So if you don't want to introduce the complexity of pressure, the Helmholtz energy is what we use. So what we know is that the chemical potential, or in our case, most specifically the partial molar Gibbs, from phase 1 is going to be equal to the partial molar Gibbs of the same species in phase 2, and so on and so forth. So the whole purpose of defining the partial molar property is ultimately to come up with our phase equilibrium criteria. This is what we established effectively in chapter 8. So moving on, chapter 9 is how do we get this? How do we calculate the partial molar Gibbs based on whether or not we have an ideal gas, a real gas, a liquid, an ideal mixture of liquids, right? So effectively we're going to be going through now a series of strategies in order to determine what's our best way to approximate the partial molar Gibbs. What experimental data do we need? What sort of equation of state do we need? What kind of assumptions do we need to use when applying an equation of state in order to calculate the partial molar Gibbs? How are we on that? Does it make sense? Do we feel like this is an important pursuit?
Important pursuit.
The short story, though, is we're not actually going to be calculating this, really. We're going to be calculating what we call partial fugacity. And if you see on the handouts, that's what we'll get to today, a bunch of complicated-looking integrals in order for us to come up with an approximation. So we'll find that the partial fugacity is equivalent across all the phases, exactly the same thing as how the fugacity is equivalent across all the phases. So to start off with, we are going to go simple. Ideal gas mixtures. So the basic premise of an ideal gas is that the molecule density is so low that there is zero interaction between any of the molecules in the system. Right? So it doesn't matter if I have a system of only A molecules, only B molecules, or a mixture of A and B molecules. Doesn't matter. The fluid will behave exactly the same if it's an ideal gas. I mean, they'll have different heat capacities potentially, but in terms of the pressure-volume relationship, right? Nothing in here says anything about what the compound of the molecules are. Temperature is the temperature, R is R, pressure is the pressure, specific volume is potentially what we'll be solving for, right? So what this means here, the number of moles of gas in the system is just equal to the summation of all of the number of moles of each of the individual subspecies. What we can deduce then is that the total internal energy of an ideal gas, U ideal gas mixture, so this is oftentimes the notation we're going to be adopting today, IgM, ideal gas mixture. IM is going to correspond to ideal mixture. We'll cover what that means as approximation. And then, of course, Ig is just going to be an ideal gas. This is going to be equal to the total number of moles multiplied by the specific internal energy of the mixture, which is going to be a function of temperature, pressure, and composition of the system. And based on the approximations that are in the ideal gas law, or the basic fundamental assumptions of it, this is simply going to be equal to the summation of the number of moles of, let's say, species J, multiplied by the specific internal energy of that subspecies A, which is, again, only going to be a function of temperature and pressure because it's a pure fluid itself. Everyone's on the same page. Perfect. So what we want to know then is what is the partial molar internal energy for an ideal gas mixture. All we're going to do is apply our definition of a partial molar property, where we're going to take the partial derivative of okay, so we're going to hold temperature, pressure constant, and the composition, so J not equal to I throughout this. Substitute this relationship here into our partial derivative and evaluate. Okay, so just a quick overview. The internal energy of a pure ideal gas is only a function of which two properties? Temperature and pressure. The number of moles of species J is only a function of what? It's a trick question. Moles. Only a function of the number of moles of species J. So if I'm taking the partial derivative with respect to the number of moles of species I, this term here is always going to be zero, right? The specific internal energy of a fluid doesn't matter how much of that fluid you have. So this is always going to be zero. And J is always going to be zero except under which circumstance?
I'll use it with J.
Yep, so if I is not equal to J, this all goes to zero. So the only instance where it doesn't go to zero is when I equals J. So if I is equal to J, therefore we can write that the partial partial molar internal energy of species I in an ideal gas mixture is equal to simply the specific internal energy of the pure fluid. Now, this is exactly the conclusion that we reached when we have an ideal mixture. The behavior of the fluid in a mixture is exactly the same as the behavior as the pure fluid. Now, we can do effectively exactly the same conclusion to show that the partial volume in the mixture is exactly the same as the volume of the fluid itself. Now, pressure is different. Pressure is not an intensive property. Sorry, it is an intensive property, but it is not dependent at all. There's no way we can convert the pressure to an extensive property. Right? Pressure and temperature are always going to be intensive. So the analogy here that we have for internal energy and volume doesn't apply for pressure. So instead, we define a function called the partial pressure, where this is simply the number of moles. It's the mole fraction. This is the partial pressure. So the partial pressure is something that I'm sure most everyone has heard of before. Who's heard of the partial pressure? Okay, everyone's heard of the partial pressure. It doesn't really mean a whole lot of anything. All that it means is if your fluid is an ideal gas, this is the effective contribution to the pressure that those molecules have by banging onto the wall. You cannot actually isolate the contribution of pressure from any one component relative to any other component, because you don't know why, let's say, species A is hitting the wall more than species B. It could be because that it has a greater mole fraction, or it could be that it really hates component B, and so that way component A is really slamming into the wall to get away from it. But in terms of ideal gas chemical reaction equilibrium, this is a useful concept. For real fluid relationships, we have to define something called the activity, which is what we'll get to in a couple of weeks' time. But the partial pressure is a definition. It's not an actual real physical concept necessarily. So using this information, lastly, we can also show here that the partial enthalpy of an ideal gas mixture is equal to the enthalpy of the pure fluid. And this is just from combining these two concepts and the fact that we're, in our definition of the partial property, we're holding pressure constant. Right? So enthalpy, as we know, is defined as internal energy plus pressure volume. So if we have a relationship here for this, and a relationship here for this, and then the pressure is constant, then we don't have to worry about it in our expressions. Okay. Now things get a little bit more complicated when we talk about entropy. Do we expect entropy to have an identical relationship as internal energy, volume, and enthalpy? Why not?
When you mix things, you're generating energy.
Right, it's easy to mix things, it's very difficult to unmix things. And the reason behind that is the entropy. So no matter what, even if we have an ideal gas system, when we mix two fluids together, it is not going to be the case that it's going to be just the fluids are going to behave how it would normally. Right? Entropy is always going to increase. So the way that we traditionally derive what the ideal gas entropy change of mixing is by building, again, an arbitrary system where we have number of moles of A at some temperature, at some pressure, and a chamber of the number of moles of B. And effectively what we do is we expand A into B, and we expand B into A such that the final volume of the two fluids is constant. So what we want to find, the total entropy change of the system is the entropy change of A plus the entropy change of B. So in this circumstance, we'll grab one of our combined first and second law formats. Yeah, plus PdB. For an ideal gas with constant heat capacity, we can rewrite this using some of our ideal gas relationships on the equation sheet. This one's going to be C. Ideal gas, there it is, plus R. Right. This is just substituting in the ideal gas law, taking the partial derivative, and integrating it with respect to volume. Right? So for simplicity's sake, let's say that the temperature is constant, so dT goes to 0. That way we only have to worry about the change in the volume of the system, which makes our calculations significantly easier. And so we'll also note that the volume of B, sorry, 2B is going to be equal to the volume of 2A, and we'll just call that the final volume of the system. Right? We're expanding A into B, B into A, but they're also going to be finally occupying exactly the same space. So that means the delta S of A is going to be equal to R natural log of V over V1A. I'm going to rewrite this as minus R natural log of V1A over V. Do one more step here. V of A over the total volume. Let's substitute in the ideal gas law. Let me make sure. Trying to make sure I don't mess up my subscripts up again. I'm deviating a little bit from my notes, which is always a risky prospect. 1A, B, 2A, which is equal to it's not complicated math, but I just want to make sure I don't mess up my subscripts and everything. Oh, that's what, okay, that's what I did. That's what I got. So I take one more step here, and I wrote this as minus R N A V A over B. So it's the same thing I did there, but I pulled that NA out beforehand. Sorry. Sorry for the confusion. It's not complicated, but I just didn't want to botch any steps.
You have minus R log
Yes.
NA.
Oh man, what am I doing wrong here? Okay, so when okay, let's just forget about that for right now. We'll keep it as it is here. We'll just work it out together then, I suppose. So V underbar is equal to the volume divided by the number of moles. So in this case here, V underbar of 1A is going to be equal to V over V1 over NA. V underbar of 2A is just going to be equal to the final volume divided by NA. So if we put these together, V underbar of 1A over V equal to V1 over NA divided by V over NA, and they cancel out, which is just equal to V1 over V. I just want to make sure I canceled all the NAs correctly. Because then we will substitute in our expression for the ideal gas law, where this is going to be N A R T over P divided by N R T over P. And all I wanted to do with all this math, so sorry for botching this completely, is that this is basically the R's and T's cancel, the P's cancel. I just wanted to show this to you with the mole fraction. The ratio of the specific volumes is just equal to the mole fraction. But I did a wonderful job of messing that up. That's all I wanted to show. Okay, let's leave this side of the board, it's cursed. So we can now write that the change in entropy of A is equal to, what do we have here?
Negative R.
So we can write that the specific change, right, is minus R natural log of the mole fraction of A. Or we can write that the total entropy change is minus R times the number of moles of A times by the mole fraction of A. Same thing for B. Exactly the same, but just substitute those two out. So our change in delta S is only the change in mixing. Our final state is the mixed system. Our initial state is the unmixed system. So this is effectively our definition of the entropy change of mixing. Divide the whole system by n so we can get this as an intensive property. And we can reduce this a little bit. Minus R xi ln of xi from I equals 1 to the number of components c. All right. So if we take a look at this equation, this is the change of entropy of mixing of an ideal gas for an arbitrary number of components, we can repeat this analysis as many times as we want, R times the mole fraction times the natural log of the mole fraction. Right? This is negative. That does not mean that the delta S of mixing is negative, because the mole fraction of I is always less than 1, but greater than 0. This doesn't change the sign at all. However, the natural log of a mole fraction is always less than 0. So if we take these two terms together, we find that the change of mixing in entropy is always greater than 0. It means we always have entropy increasing in a mixing process. Let us take a look at an entropy balance. Okay, this is our generalized entropy balance. In this case, I'm going to do it based on the entire system, in which case it is closed. We can say that it is adiabatic. Our ds dt, if we integrate these expressions, that gives us s of 2 minus s of 1 is equal to the total amount of entropy generated. This is going to be equal to the mixing process. We're going to start off in an unmixed state, and we're going to go to a mixed state. So that means that the entropy change is directly being entropy generated. Is this a reversible process? No, because S-gen
Not equal to 0.
is greater than 0, which means this is irreversible. Once two fluids are mixed, they can never be unmixed unless we put energy and work into the system, and ultimately we have to generate even more entropy. So mixing processes are always favorable because they always increase the entropy. Now what we can do is, by playing around with the algebra a little bit, we can add to our list of partial properties so that the entropy, partial molar entropy, which is a function of temperature, pressure, and composition for an ideal gas system, ideal gas mixture, is the pure species entropy just add to our list of things. Okay. So if we can continue on, we define our Gibbs as the enthalpy minus Ts. Temperature is being held constant during mixing processes. Right? We're mixing things at constant temperature and pressure. That's the framework. I erased it on how we defined our chemical potentials being the partial molar Gibbs. So what we can see is that we change the sign a little bit here, that the Gibbs, partial molar Gibbs of an ideal gas mixture as a function of temperature, pressure, and composition is going to be equal to the Gibbs of the pure fluid at constant temperature and pressure plus the contribution from entropy, and likewise we can also show that the Helmholtz energy of an ideal gas mixture has exactly the same expression here. Now one thing that I've noted is I put that Helmholtz is a function of temperature and pressure. Technically it is, but it's also easier to calculate Helmholtz when the volume is being specified. But that doesn't mean that it's not a function of temperature and pressure. So we can rewrite all these however we'd like. So for example, the pure fluid properties, I keep on tending to write temperature and pressure, but it's really any two intensive variables. Gibbs is most easily calculated at constant temperature and pressure. Helmholtz is most easily calculated at temperature and volume, but that doesn't mean it's not a function of those two. So what this means is that if I take the Gibbs of a pure species and I want to put it into a mixture, the least amount of complexity that I can have in this system is for an ideal gas mixture, which means that I have to add in this contribution. R is always positive, temperature is always positive. The natural log of something that is less than 1 is always negative. So this term here, Gibbs, I mean, it doesn't have to be positive because you can choose a different reference state. Gibbs could be negative, it doesn't matter. Let's say, for example, this is positive, this is going to be negative. So in this case here, the partial Gibbs of species I is always going to be less than the Gibbs of a pure species because the mixing process is always going to increase the entropy. If you increase entropy, you're going to decrease Gibbs. So mixing processes are always favorable under all circumstances. And this has some very important conclusions. Okay, so are any questions on this? Sorry I botched the math a little bit, making it confusing. It wasn't any confusing math, it was really just making sure the algebra notation I took was appropriate.
One quick question.
Yes?
As the delta S of the ideal gas, would that be per mole?
Yeah.
Delta S?
Sorry, yes.
Okay.
Intensive properties. If you times everything through by n, it would come to
Yeah,
the same
then it would be
conclusion.
the same. Okay.
So the complexity is that there's so many different ways to write these equations. It all just depends on making sure I derive the one that I am prepared to explain. All right, so let's take a look at the Gibbs of the system. If we are to look at what is the total Gibbs free energy of a system, mixture system, temperature, pressure, composition, right? So it's a function of everything. This is equal to the summation of the mole fractions times by the partial molar Gibbs, which again are a function of everything. The Gibbs then is going to be equal to equilibrium then is going to be based on competing enthalpic versus entropic forces. So let's envision a situation where I'm going to draw out this function. Let's say we have a mixture of oil and water. Right? It doesn't matter. We can choose whichever compound to represent oil. Let's say it's a long chain alkane like decane. Does decane and water like each other?
No.
So if I were to mix those two fluids together, would I expect it to be endothermic or exothermic?
Like to actually get them to mix,
Sure.
it'd be endothermic.
Okay, so why would it be endothermic?
Because
That's
that's
a
the
use
thing.
energy to.
So if I have water and water, right, they really like each other,
You have to break all those hydrogen bonds.
right? Yeah, so basically, so water and water like each other. Let's say decane and decane. Well, they really like each other too. So this is going to have, let's say, some negative energy, right? A really low energy state. It's going to be nice and stable. This is going to be negative. It's going to be really low, really stable energy state. Decane really likes decane, water really likes water. Now, if I mix the two of them together, and I am forcing water and decane to interact, they're going to not like each other, which means it's going to take energy to get them to be nearby one another. Now, the energy that it's taking them to be like and near each other, right? So I'm breaking all these hydrogen bonds, right? But then here, I need to have a ton of energy to get these two fluids to stay together, because otherwise they don't want to be that way. So the system cools down to give it that energy. Now, in contrast, the sulfuric acid and water scenario, sulfuric acid and water really like each other, right? So they go from a negative and negative to really negative, right? So that means energy is being released. So when two fluids don't like each other, it's endothermic. So as a general rule of thumb, most all mixtures are going to be endothermic mixtures. Now, the reason why we don't see that as often when we do our chemistry experiments or our thermodynamic experiments, because there's not a lot of fun to mix stuff that doesn't want to mix, right? We typically work with things that do want to blend together. Otherwise, we can't get them to dissolve, we can't do reactions, we can't do any chemistry. So in general, right, we don't see endothermic mixtures as commonly, but most fluids, if I grab any two chemicals off the shelf randomly in the Fisher catalog, they're probably going to be an endothermic mixture. Just as a general rule, because most fluids don't like each other. So that means if I were to look at the Gibbs, and let me write out, let's see if I have a different color here, the enthalpy of the mixture, right, which is going to be just this term right here, summation of xi, over bar I. They're not going to like each other, right? They're going to have a positive delta S, positive delta H. So if we had no entropy in the system, that would mean that our Gibbs free energy would increase when I mix them. So why would they mix? Right? So if I try to come up with a solution here, that's got a higher Gibbs free energy than my reference state. Right? Here is 0 and 0. So the lowest free energy of the system is if the two fluids phase separated and said, no, I'm just going to be pure. I don't really care. Does that make sense? This is a higher Gibbs free energy than my reference condition. I can choose my reference arbitrarily. So you'll notice that in the future, all of these pure species and mixtures, we're always going to set the reference to 0. So whatever the temperature and pressure that we're mixing at, we're just going to say Gibbs is equal to 0 to the pure species. H is equal to 0 to the pure species. S is equal to 0 to the pure species. It allows us to draw these nice, pretty charts here. Now, grab a different color for entropy. I have another one here. Green. Let's see if this works. Let's also draw out the entropic contribution to the system. So now we have to plot this function here. Now here I've just drawn some sort of arbitrary function. I don't really actually know what the shape of this curve looks like. It could be more complicated. But instead, we're going to plot out the ideal gas mixture function for the entropy. And what it looks like is something like this. However, if I were to take the limit of this expression, so the limit as x1 goes to 0 of the summation of x of I, ln x of I, we can add an RT in here just to be thorough. This actually turns out to be, let's see, so limit here. Well, it does go to 0. That doesn't actually help very much. Oh, shoot. The limit here. It does go to 0 eventually, but what I'm looking for here is the slope, rather. I gotta update my notes on this one. I'm not keeping track of my own stuff here. But anyway, the slope here is actually what I'm trying to get access to. The slope approaches negative infinity. If we were to look at the derivative of this here. And likewise over here, the slope approaches positive infinity.
can see from there.
Oh,
The green.
The green, yeah, the green's not that
Yeah,
fast.
really faint there.
Let's see if I have another green one, see if that's a little bit better. No, that's first. That didn't work out. So I'll show you this here. This is positive infinity
Okay, cool.
slope. And this one here, the slope is negative. So you have to use L'Hopital's rule and play around a little bit with it. But effectively, it approaches it with infinity. So if we're trying to assess whether or not oil and water, or let's say decane and water, mix, if we zoom in this region here, we have a contribution to the free energy that increases from enthalpy, right? They don't want to mix enthalpically, but we have a decrease of free energy entropically, saying they do want to mix. So whether or not they will mix, at least to a dilute quantity, does the rate of free energy increase from the contribution of enthalpy cause the system to increase, or does the rate from entropy cause it to decrease? Oh, here, this is why. Sorry, I just had my moment of brilliance here. So the partial Gibbs, right, for species I, is how it changes with respect to species I, which we can break it down into the enthalpic and entropic components. So if we break this down here, we're looking at effectively okay, sorry about that, guys. That's why we care about this. Partial Gibbs, which is equal to the chemical potential for our system, this determines whether or not the fluid is in equilibrium. If we substitute in the definition for the Gibbs, we can see that this is equal to the partial enthalpy and the partial entropy, but the partial entropy is not necessarily the entropy itself, it's the rate of change of the entropy, whereas in the enthalpy, it's the rate of change of the enthalpy. Does that make sense? Have I lost everyone? Okay, we're good. Sort of. I see a lot of blank stares. So the complication here is that the partial Gibbs is what we care about for phase equilibrium for species I, has the partial enthalpy contribution and the partial entropy contribution. Now if we plot out what is the Gibbs as a function of enthalpy and entropy, the partial Gibbs is going to be the slope here. So the slope here is going to be the partial enthalpy of, let's say, species A, and the entropy, I'll just use black. The partial entropy here is the slope of the entropic contribution. We'll do this again on Friday. So whether or not these two fluids will mix is going to be whether the slope of the rate of increase of enthalpy is going to be overcome by the rate of slope decrease of entropy. Now because this function here, if we take the partial derivative, now we have to do a little bit of math substituting n into the x's, which gets a bit tedious. You'll do this on a homework problem or two. Right? We'll find out that this approaches negative infinity as the number of moles of species A goes to 0, or as the mole fraction of A goes to 0. So what the conclusion of this is, let me draw it out in a slightly different way here, is that if we are to zoom in of the Gibbs as a function of the mole fraction, you will always have a decrease than an increase. Always. Because no amount of repulsion here will ever counteract the negative infinity slope of the entropy in a dilute system. So the consequence of this is that everything is partially miscible in everything else, according to the second law of thermodynamics. So no matter how much these two molecules dislike each other, a little bit of oil will always dissolve in water, and a little bit of water will always dissolve in oil, because entropy says that the free energy of the system will always be lowered if you add a little bit of species A into a sea of species B. And there's a way to think about this here, because if I take one molecule of A and I put it into a volume of B, I've effectively given that molecule an infinite room of space to move around in. So you will always have entropy gained that way. Do we agree or disagree? So one example is if I took a water bottle and I put some motor oil in it and I shook it up, no one would drink that water, even if it looked clear, right? Because you know that a little bit of that oil is going to dissolve into the water. So, this also poses a second problem. The partial molar Gibbs, which determines all of our phase equilibrium behavior, has a discontinuity in it. Because as x goes to 0, or the mole fraction goes to 0, your entropy diverges. It either goes to positive or negative infinity, depending on whether or not you're looking this way or that way. So even in the simplest ideal gas scenario, you have a discontinuity in the most important property that we have to worry about with respect to phase equilibrium, the partial molar Gibbs, right? Entropy of a dilute system, the partial entropy of a dilute system, goes to negative infinity. Right, so that basically means then that we have a problem. Right, so we need to fix it in some manner. And so what we do is we define the partial molar Gibbs free energy, which is what this sheet is here. Fortunately, I bumbled my way through this lecture, so I can't kind of go through the derivation. We can talk about it in class, but rather what we'll do instead is just move on from here, skip over the derivation of the partial molar Gibbs, partial molar fugacity, and effectively just apply some of the exact same relationships that we already have. So I'm going to skip over the step of why this is true, but what we can say is that we can write that the Gibbs free energy changes this is an expression, this is just the combined first and second law of thermodynamics that we've seen many, many times over again. So we've expanded the Gibbs with respect to temperature and pressure. What we're going to say now is we're going to follow a path of constant temperature and constant composition of the system by varying the pressure. So in that case, we can say that the Gibbs free energy of species I at sunk temperature, pressure 2 composition is equal to the Gibbs of temperature, pressure 1 composition. We're going to call this 0. And this is going to be the integral from P1 equals 0 to P2. So effectively what we're going to do is this is exactly the same approach that we used to derive the fugacity, but in this case, instead of having underbars, we have overbars. So I skipped over the rationale for why we can just simply replace the overbars with underbars, but the good news is that every other derivation that we've done so far, it's worked out such that you can just swap those two out. And that's going to be the case. That's the reason why we established the partial molar property the way that it is. These are all the relationships that we have hold true for mixtures versus non-mixtures, the first and second law rather. So this is exactly the same approach that we took to define the fugacity in the first place. Right, so what we need now is a relationship here. So we jump straight into the definition of the fugacity then itself. So we define the partial fugacity, which is a function of temperature, pressure, and composition. We define it exactly the same way that we define the fugacity, but in this case, rather, it's the partial Gibbs minus the Gibbs, oops. Where's my sheet here? Yeah, I'll write this differently. I'll write it as I have it on the sheet. Okay, and that's where we'll stop today. So what we've done in defining the partial fugacity in the way that we've done so is we want to get access to the partial Gibbs of species I. We're going to do that through a term called the partial fugacity. What makes our lives easier and why the whole reason why fugacity is defined in the first place, right? We didn't have to use fugacity to solve anything for a pure mixture. But this term right here, the partial fugacity of species I in an ideal gas mixture, has this problem here, where it goes to negative infinity as you get to a dilute system. But since we know that all ideal gases behave this way, we're eliminating that complexity in the partial fugacity. So all that we care about is the deviation from ideal behavior. Now we can calculate that using an equation of state, provided, right here, we know how to calculate the partial volume of an ideal gas mixture. Right, we talked about at the start of class. All we need now is a temperature-pressure composition relationship for the partial volume of a fluid in a mixture, and that tells us everything we need to know about the phase behavior of the fluid in a multi-component, multi-phase system. A lot of blank stares. Okay, so now the only challenge is how do we get this from an equation of state? And rather, if we can't get it from an equation of state, we get the partial fugacity from an activity coefficient. So either we need an equation of state that can calculate this property, or we will use experimental data to calculate the property to figure out how it's going to behave in a phase equilibrium system. Okay, but the key concepts to remember here is most specifically that when you have a dilute system, the entropy always causes it to mix. So entropy always causes a mixing process. The enthalpy can never overcome that in a dilute system. So all real systems that don't want to mix will look like this. This composition here could be on the order of parts per million, parts per billion, parts per trillion, but you will always have a little bit of something dissolving into something else. Like how much does a gold nanoparticle dissolve in water? How much does a rock dissolve in water? How much does the table dissolve into the air? Right, so everything will have a finite vapor pressure. So this table, in theory, will eventually evaporate. Very, 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 very slowly. Right, but according to thermodynamics, it has to. This phase has to dissolve into this phase. Otherwise, entropy, the second law, is violated. All right. I'll put you out of your misery. See you all on Friday. I'll post another homework today or tomorrow. An exam will be 1 week from Friday.